Thank you. At the Ethical Society, we organize our programmatic year around a theme, and this year's theme is Exploring the Human Condition. I hope that you've enjoyed the diverse platforms these last few months. The platform team is hard at work scheduling dynamic speakers with fascinating topics for us in the coming months. Today's speaker is a professor of physics emeritus. I'm never sure if that's how you pronounce that word, but you know what I mean, right? At Washington University, and a former deputy director of the Institute of Theoretical Physics at Santa Barbara, California. He received his PhD from Harvard University, where he studied theoretical high-energy physics under the direction of Steven Weinberg. With biologist Ursula Goodenough and geologist Michael Weissession at Washington University, Dr. Bernard developed a course called The Epic of Evolution and taught the cosmology and astrophysics part of the course for many years. He was raised in the ethical culture movement, having graduated from the Long Island Society Sunday School in 1964, and has been a member here at the St. Louis Ethical Society since 1991. Please join me in welcoming Dr. Claude Bernard to the stage.
Good morning. Thank you, Nikki, for the introduction. And thanks to Claire for the great music, and thanks to Joan for her wonderful words setting the mood for us today. And thanks also for 25 wonderful years of marriage. So let's just jump in here. I'm going to talk about the possibility of other intelligent life in our galaxy. Our galaxy is the Milky Way. This is a view from the southern hemisphere and towards the center of the Milky Way. There's a lot of stars there. This is a view, a simulated view, what it would look like from outside the galaxy. And it's big, 100,000 light years across, and there are about 200 billion stars in our galaxy, and the sun is just some tiny little dot over there in one spiral arm. And of course, there are plenty of other galaxies out there. This is a view of a tiny region of space by the new Webb Space Telescope. Almost every dot in this picture is another galaxy. There's some stars that are in the foreground, but almost all the dots are galaxies. And there are at least 100 billion other galaxies in our observable universe. Some people think maybe more like 1 trillion, but at least 100 billion. But I'm going to focus on the Milky Way, and as you'll see, the reason is that the Milky Way itself is already immense, and there would be huge difficulties in communication or transportation between star systems. And if you try to imagine what you would need to contact civilizations outside our galaxy, the difficulties would be hugely greater. So it's hard enough within our galaxy, and I'll focus on that. But you have to keep in mind that if there is some other intelligent life in our galaxy, there's probably creatures everywhere in the universe that maybe we will never know about, but may be there. So it's a very interesting idea. So we're going to wonder about life on planets outside our solar system. Such planets are called exoplanets, planets orbiting other stars than our sun. And the first exoplanet was only discovered in 1992. It's a recent subject. And By now, more than 5,500 of them have been found. Now, you might think that you would use the direct method, get a big telescope and look for these other planets. Usually, however, that doesn't work. Stars are about 1 million times brighter than the planets that surround them, and so you'd have to block out the star's light, which is difficult, in order to see the planet. In addition, planets are a lot smaller than stars, and on a cosmic scale, planets are very close to the stars, so it's hard to resolve the planet from the star. So the direct method has only been successful for nearby stars that happen to have big planets orbiting relatively far away. And here's an example. Well, only 1% of exoplanets have been found this way. Here's my example. Oops, sorry, went back too far. Sorry about this. Here's an example. The star is in the upper left-hand corner, and you can see 2 planets down towards the right. This is a star that's 11 light years away from us. So most exoplanets have been found in other ways, indirectly. And one method is what I'll call star wobble. Here's a simulation of a star in the middle and a planet orbiting it. When the planet orbits, the star also moves, pulled by the planet's gravity, and it wobbles a little bit like this. Is a little bit of an exaggeration because this planet is close, but that's the general idea. Star wobbles, and that wobble can be detected. It can be actually detected by the change in frequency of the star's light as it goes towards us and away from us by the Doppler effect. So that method is good for big planets orbiting close to a star, and about almost 20% of exoplanets have been found this way. The second method is what I'll call transit. And this is the idea that when a planet passes in front of the star as seen by us, then the star's light will be temporarily slightly reduced because of the planet in the way. And this is a simulation of what it would look like from outside our solar system if Jupiter is passing in front of the sun. And that little bit of light being blocked out can be detected. The star gets dimmer for a while and remains dim as the planet moves across, and then becomes brighter again as the planet goes around to the other side. And a couple of satellites in the last decade and a half have found thousands of planets this way. And about 75% of known exoplanets are found this way. And then there's some other indirect methods, which I won't talk about. They only cover about 5% of the planets discovered. So there are lots of exoplanets out there. What about life on them? Well, and it seems likely that most stars have planets. What about life? What does life probably need? Well, pretty clear it needs complex chemical reactions to reproduce, to grow, to metabolize, to respond to stimuli. And for these chemical reactions, the carbon chains as a backbone with other elements attached like hydrogen, oxygen, nitrogen are hard to beat for their versatility, their stability, and their reactivity. And here's some examples of carbon chains. Glucose is a sugar with a carbon ring and with some oxygen and some hydrogen and oxygen around it. That's a sugar. Here is glutamine, which is an amino acid that our body uses to make proteins. It's basically the same idea, carbon chain, hydrogen and oxygens, and a couple of nitrogens. Now, carbon is common in our galaxy, and so that's probably not a limiting factor for life. What else does life need? Well, the other main thing it needs is a liquid environment. In a solid, it's hard for chemicals to move around, so that doesn't work very well. And in a gas, things are too diffuse, things fly apart. So you need a liquid, and liquid has to dissolve a wide range of substances, but not destroy them. And it's hard to beat water for that purpose. There are other possibilities that have been suggested, and it might work, and might even be some life that's based on them, but it's probably much rarer. One liquid that's been suggested is ammonia, and that always reminds me of one of my favorite cartoons. I don't know if you can see it. Here's a spaceship that's crashed in the desert, and this poor little ET is crawling in the sand with his tongue hanging out saying, "Ammonia, ammonia." Other liquids that have been suggested are sulfuric acid, liquid nitrogen. It might be possible, but it looks quite difficult. Water really is the best. And I'm just going to assume that water is a necessary ingredient. Liquid water is a necessary ingredient for life, or at least most life. So if we're going to have liquid water on our planet, what does a planet need? Well, the planet should be in what's called the habitable zone. And the habitable zone just means it's not too close to the star where it's too hot and water boils, and not too far from the star where it's too cold and water freezes. And for a sun-like star, shown here, you have the star in the center, some red area where it's too hot, some green area where you can have liquid water, and then some blue area further out where it's too cold. And Earth, in our case, is right in the middle of this green area. If the star is hotter, then the green area will be further away. And if the star is cooler, then the green area will be closer in. But there's always some green area. And this green area, the habitable zone, is also called the Goldilocks zone. Not too hot, not too cold. So I would say the habitable zone is pretty much a minimum requirement for life to evolve, especially for complex multicellular life to evolve. There may be other requirements, and I'll talk about that later, but being in the habitable zone is kind of a minimum that you need. So now I come to Frank Drake, important figure in this field. He was a pioneering radio astronomer, and he was one of the first to use radio telescopes to search for signs of intelligent life elsewhere in the universe. And in 1961, at a conference on this search, where other famous people were in the audience, including Carl Sagan, Philip Morrison, he wrote down something which is now called the Drake equation, which is a way of estimating, or at least thinking about, possible number of extraterrestrial civilizations in our galaxy that we might be able to communicate with, or maybe detect indirectly. So I'm going to talk a lot about this Drake equation with the idea of estimate. How many civilizations might there be out there? Now, as you'll see, there's a lot of factors in this equation we don't know, or we can only make educated or flimsy guesses about. So you should think about it more as a way to think about what's needed for extraterrestrial life rather than an actual prediction of how many civilizations there are out there. Nevertheless, I'm going to think through it in detail. So we're going to call the number of civilizations, this is in our galaxy N, that are supposedly they're right now able to communicate with us, or might if we listen hard enough. And it's certainly going to depend on the number of stars in the universe. Every star gives you a chance to have life, so it's going to depend on the number of stars, but then those stars need to have planets, so we'll multiply by the fraction of stars that have planets, F planets. And then even if it has planets, the planets would have to be in the habitable zone to have life. So I'm going to multiply by the average number of habitable planets in a star system where there are some planets. And even if it's habitable, maybe life won't develop. So we need the fraction of habitable planets in which life actually develops. Okay, so that's where we're so far. Bear with me, this equation is long, but it has all the features, and I hope you'll kind of understand where everything's coming from. Now we have life, supposedly, but we need to know or multiply by the fraction of cases where intelligent life evolves out of the simple life that we had to begin with. And then if we have intelligent life, that might not be enough, because intelligent life, there are plenty of animals that are intelligent. Dolphins are intelligent, but they don't have a civilization with technology that might be able to communicate with another civilization. So I'm going to multiply by the fraction of cases where intelligent life develops a civilization with technology. So that's the fraction. And now there's one more feature. Well, they might communicate with us. They might travel here for a visit, perhaps. Maybe just be observed passively by us. But there's one more factor that we have to consider. Just because such a civilization evolved doesn't mean it's there now. How long does such a civilization last? Are they there now, or did they die out already? We have to multiply by the years that a civilization is active on average, divided by the total age of the galaxy. That's the fraction of them that would be around now, as opposed to some other time. So that's our final equation. There it is. All those factors are important, and we'll talk about them. But for now, I want to plug in some numbers just to get a feeling. And as you'll see, I already mentioned some of these things we know pretty well. Other things are, stabs in the dark with rather flimsy justification, as you'll see. So here's some things we do know. The number of stars is about 200 billion. The research on exoplanets have shown that just about every star has planets. So I'm going to say all of them have planets, roughly speaking. And again, the research indicates that planets in the habitable zone are not that unlikely. I'm going to say that if a star has planets, maybe half the time it has a planet in the habitable zone. Now, if the planet is habitable, what's the chance that life actually develops? Okay, well, we don't know. But one thing that makes me think that that is probably very high is that life formed very early in the Earth's history. So that suggests that it's not that hard for life to form once you have the right conditions. As soon as the Earth cooled off, basically, life began. So maybe it's not that hard. So I'm going to put in the fraction of cases where life evolves on a habitable planet is near 1. Now, getting intelligent life is much harder, and it took a lot longer in Earth's history. The first multicellular life took about 3 billion years to evolve. The first vertebrates took about 4 million years after the Earth formed, and intelligent life is much more recent. So I'm going to assume that only 1/10 of the cases does intelligent life eventually evolve. We don't know. And what fraction of intelligent life develops technology? Well, this one I really have to pull out of my hat. Here's my flimsy reasoning. I'm going to list animals that are smart and see how many I come up with. So I came up with crows, dolphins, elephants, dogs, and humans. 1/5 of them have technology. Now we can argue, I don't want to get into the dog versus cat thing. There's also octopuses, certainly. There's other smart whales. I don't know. You may come up with another 5, but roughly this is what I came up with. I have no idea whether this is a good way to estimate it, but we need something to put in, so that's what I'm going to put in. And then finally, how long does a civilization last on average? Well, we have no idea. We're here, and we haven't gone away yet. So I'm going to pick a optimistic number for this first. People like us, or creatures like us, these were not humans, but proto-humans, already existed 4 million years ago. And I'm just going to say, well, if we've been kind of around for 4 million years, let's assume we last another 4 million years. And we'll see other possibilities later. And the galaxy A, as we know, it's about 10 billion years. So if you put in all those numbers, what do you find? You find that there are close to 1 million other civilizations in our galaxy there now, if you take these numbers at face value. 800,000. Okay, that's a lot. So that's very interesting. And we come now to Enrico Fermi's question. Enrico Fermi is one of my idols in physics. Great guy. For the first half of the 20th century, Nobel Prize, first atomic reactor, part of the Manhattan Project. You may not know, but the particles that make you up, protons, neutrons, or electrons, are called by physicists fermions. Particles of matter are fermions because of Fermi's work, understanding them. So, and Fermi loved to kind of think about questions like this, you know, with numbers. He could even do these in his head. And already in 1950, before Drake, 10 years before Drake, he was thinking about this, and I don't know his exact reasoning level, but sort of must be similar to the Drake equation. And he went through it and found, oh my gosh, there's a lot of possible life in our galaxy. And so he asked this question, but where is everybody? And that's called Fermi's question, or Fermi's paradox. If there's so many out there, where is everybody? So I'm going to discuss some possible answers to that question. And of course, we don't know the answer to that question, but let's discuss what are the possibilities. So the first answer is, well, they're here. You know, we've heard about things called UFOs. Now they're called UAPs. They've been renamed because UFO is kind of a restrictive thing and also has a lot of baggage with it by now. They're called UAP, unidentified anomalous phenomenon. Might not be an object, might be some atmospheric phenomenon. Anyway, they're UAPs now, but maybe they're here. Here's a picture of a flying saucer over Passaic, New Jersey, 1952. To me, that looks like a hoax, but I don't think this particular picture has been proved to be a hoax. Just looks like it, but I don't know. Many UFO sightings or UAP sightings have simple natural explanations: meteors, aircraft, weather balloons. Some indeed are hoaxes. Here's a famous example, a flying saucer here, you may not be able to see it very well, being held by a soldier who recovered it in Twin Falls, Idaho in 1947. And this was supposed to be a flying saucer from outer space, but it was soon found that it was a hoax made by 4 teenagers out of pieces from an old jukebox. Here's another one. This thing This picture was taken in Belmore, New York, 1967. And in this case, I actually know that this is a flying saucer because I took the picture myself. But the saucer it is a Frisbee, looked edge on. Now, some of these have been secret military programs that the government doesn't want to acknowledge, and that's led to all kinds of speculation. And the most famous one of those is Roswell, New Mexico. And here's a picture of a soldier again with some of the recovered debris from Roswell, New Mexico in 1947. And when this debris was found, so this thing was actually a secret government program, a balloon that was supposed to detect Soviet nuclear tests. And they didn't want to acknowledge that they had this technology to look for Soviet nuclear tests, so they had to make some other excuse for what it was, and some not very bright person in the Pentagon initially said, oh, it's just one of those flying saucers. So in 24 hours, the outroar was so great that they had to back off on that, and they said, oh, it's just a weather balloon, which was closer to the truth, but not the truth. And that's led, all of those lies, of course, led to conspiracy theories persisting to this day. But there certainly are unexplained sightings by probably reliable witnesses, multiple ones, and some with radar signatures and so forth. So there's things out there that we don't understand. And in fact, a recent NASA panel proposed that we put more energy and money into this to look for, study them more scientifically and look for scientific explanations. On the other hand, could they be ETs? Is it plausible? Well, if they're ETs, then that means they had to come here from some other exoplanet. So let's talk about space travel for a minute. And I'll do it from our point of view. Suppose we want to travel to some other planet. So the closest star other than the sun to us is Proxima Centauri. And here's a picture. Again, it's in the southern sky, and it's a tiny little dot right there that you probably can't see. It's a mere 4.2 light years away, or 25 trillion miles. It has 2 planets, at least. Can we visit them? Well, let's imagine getting in the Apollo rocket and heading off to Proxima Centauri. Apollo rocket goes at 25,000 miles per hour, pretty good speed. At that speed, the trip would take more than 100,000 years. So it's difficult. Another way, let's think about the Voyager 1 satellite, launched in 1977. It's going faster than Apollo by quite a lot because it got some slingshot effects flying by Jupiter and Saturn, and it's gone further than any other human-made object. And you may know it has this famous golden record made by Carl Sagan and collaborators with human and animal sounds and pictures and music from Bach to Berry. That's Chuck Berry. It's now gone 12.6 billion miles from the sun, which sounds like a lot, but that's only 0.002 of a light year. It will be 20,000 more years until it leaves the solar system. So, it gives you an idea of how hard this is. And if you wanted to make the trip even to the closest star in a human lifetime, the speed required would be so much, much, much greater than current technology, and there are enormous difficulties. I'll just mention one. When you're going that fast, the interstellar dust, little particles of dust, each act like a landmine because you're approaching them with extremely high speed, so you're constantly being bombarded, and the shielding needed would be enormous to protect the spaceship and the people inside. So to me, it's implausible that aliens have the technology to come here only to crash in these various sites that people have claimed to see some crash. So they got here, but they didn't make it all the way. You know, I mean, like if they're going to come here and tap dance and fart, why go to Roswell? Why not go to Washington, D.C.? They'd fit right in. So it's also implausible to me that they've come visiting, but somehow without giving definite proof, except, I mean, they've been cited, so-called, by many people, but somehow we never have definite proof, and it's implausible that they come visiting, but somehow many governments in the world have conspired to keep it secret. It's not just our government. It would have to be, you know, many governments, and we don't have a very good record of keeping things secret. So you can imagine how, and especially something so earth-shattering as this. So I don't think it's aliens. Well, if they're not here, maybe they're there. We just need to look. And this brings us to the SETI program. SETI stands for Search for Extraterrestrial Intelligence. And the most promising way to look is with radio waves. And the first modern SETI observation is by our friend Frank Drake in 1960, using a radio telescope in West Virginia. And he observed two nearby stars that were likely to have planets. And he didn't find anything, no ETs. Some big SETI projects that are going on right now, Breakthrough Listen, it's funded to the tune of $100 million by an Israeli entrepreneur, and it's been online since 2016 using big radio telescopes, one in Virginia, one in Australia, but no ETs found yet. Here's another one, the 500-meter aperture spherical telescope. It's a half a kilometer across in China. It's the largest radio telescope in the world. And they've been looking since 2020. No ETs found yet. So maybe they're out there, but they're hard to find because, well, we haven't been looking long enough. That's one possibility. The signals are weaker than we can detect yet, quite likely. We don't know what frequencies to search. That's a big one, because there's tons of, you know, electromagnetic frequencies can be anything. There's an infinite number of electromagnetic frequencies. How do we know what to search? Or maybe they don't want to be found. There is that possibility. So one useful way of thinking about it is to turn around. Suppose you imagine a civilization with our current technology, and they're not too far away, and they're trying to detect us. Can they detect us? They'd have a hard time, even from nearby. The best shot, it turns out, it would be if they lucked into looking at broadcast TV signals. That's the best, penetrating that with the most power. That would be the best way. They'd have to be within 75 light years away from us because we've only been broadcasting TV for that long. So light takes time to get places. They have to be within 75 light years. So if that's the case, this is probably what they know about us. And given that, I think we know why they might be ghosting us. Okay, so I talked about they're there but hard to find. That's a possibility. The last possibility is they're not there because it's much less likely for intelligent life to evolve than we assumed, or technological civilizations don't last long, or both. So here's what we had before. These were the numbers, and that's what gave us this almost 1 million civilizations in our galaxy. But some of these are suspect. Maybe the number of habitable planets and intelligent life probability, maybe these are much smaller. And this goes under the name of the rare Earth hypothesis, saying that the conditions on Earth are extremely rare and they're all needed for intelligent life to evolve. So let's look at that a little bit. I assumed to be habitable, it just had to be in the habitable zone, but there might be more requirements. Life on Earth uses heavier elements than just the ones I mentioned before, phosphorus, sulfur, calcium, all the way up to iron. So maybe we need a rocky planet. But most planets are big gas giants like Jupiter, not rocky planets like the Earth. And also, to get enough heavy elements, it probably need to form recently, so the previous stars had a chance to make those heavy elements. So that's some restrictions. In addition to maybe needing a rocky planet, maybe you need the right size of star. If it's too big, you get too much ultraviolet radiation, which could destroy the atmosphere and kill life. And if it's too small, an interesting thing happens. Just like the moon going around the Earth, it locks to the Earth. So one side is always facing the Earth. A planet close to a star would lock with one side always facing the star. And that would mean that star would be very hot. That side would be very hot, and the other side would be very cold. So although on average it has the right temperature, it doesn't work. One side's boiling, the other side's freezing. And the star should be in the right place in the galaxy. Most stars are in the center, but that's not a good place to be. There's too much X-ray radiation from the black hole in the center. So most stars get eliminated. So I'm going to say maybe this fraction of habitable planets goes from 0.5 to maybe 1,000 times smaller. Of course, again, I'm pulling this number out of my hat here. With the revisions on what it means to be habitable, I'm just going to assume that if we just re-understand what it means to be habitable, then life, like on Earth, should evolve relatively rapidly. So I'm going to keep F-life as 1. But there could be more requirements for complex life and then intelligent life to develop. And mainly these are to assure that the environment remains hospitable and stable for long times, the long time it would take for intelligent life to evolve. And one requirement there might be that the planet be of the right size, large enough to keep an atmosphere and have a magnetic field to shield against the stellar wind. And then there are other ones. I won't go into detail in the interest of time, but there are other requirements. So there are lots of possible requirements for this, and I'm going to assume that the fraction of intelligent planets with life that have developed intelligent life is much smaller, so 0.0001. So I'm going to put those numbers in, and then our 800,000 changes to 0.8. About 1, which means maybe we're the only one in the galaxy, or if there is another one, it's very likely quite far away, maybe 50,000 light years. That's going to be very difficult to find. And we didn't even talk about this, years active. It's another fraught estimate. I was generous before, but we've only been emitting potentially observable signals for 100 years. So maybe we're lucky to go on for another 100. Looking at the way the world is now, maybe that's not so crazy. And if that would be the case, I would replace the 4 million years with 200 years. And then the 0.8 becomes 0.0004. So very unlikely, and means it's very unlikely that we're here at all, but here we are. Had to be somewhere. You know, but the numbers in cosmology and in astrophysics are so big. Even if it's this probability in our galaxy, there's so many galaxies out there that would say, even with that number, there would be 4 million other civilizations, technological civilizations out there now. But they're very far, they would be very far away, spread out over the observable universe. Almost impossible, I won't say impossible, almost impossible to ever get evidence of that. So, this Drake equation, I remember, it's not a prediction, it's a way of thinking about what you have to think about to worry about intelligent life. And when I think of these different kinds of conclusions you can draw from it, I always are reminded of this quote by Mark Twain, who said, "There is something fascinating about science. One gets such wholesale returns of conjecture out of such a trifling investment of fact." Okay, so now my conclusions. So are we alone? Well, you know the answer. We don't yet know. We may, in fact, never know. I would say that either of the possibilities is awe-inspiring. To me, it's awe-inspiring to imagine that our Earth is unique in our galaxy or even in the universe. And the first thing that I think about when I think about that is the Sikh core value that we just heard before. I cherish the Earth and all life upon it. And if it's unique, there's that much more reason to cherish what we have here and not to destroy it. On the other hand, I also found the opposite awe-inspiring, to imagine that we may communicate someday with intelligent life elsewhere. What will we learn? What will we find out? You know, what will we know? So both of those are awe-inspiring. Right now, we need to embrace the mystery. And I just conclude by saying, thinking about either possibility gives me goosebumps. Thank you.
Okay, wow. That's a lot to think about.